All right, so now we're going to talk about trigonometric integration and completing the square. So we have quite a few methods in this lesson, all right? And it's going to take a little while, and it can be really confusing at parts. So again, as always, the biggest question is how do we know what method to use? And to be honest, some of this is just going to have to be practice for you, all right? You got to be able to recognize patterns, and those patterns hopefully would lead you to doing the right way. Now, the main thing to understand is that if you do a certain method and you don't get it right or you get stuck, assuming that you haven't done all the algebra correctly and all the integral stuff correctly, well, if that doesn't work, then try something else. All right. So this is not something that I just look at a problem and I know immediately what to do. All right. So here's the main thing to remember though. On this part right here, you're going to have to remember all the trig identities, the Pythagorean ones and the double angle ones. So all those are just, what do you call them? They're just trig identities, right? So that you must remember, or at the very least, you should have those out beside you while doing the homework. Two important antiderivative rules that would save you time are these two, right? And they do appear in the notes and probably on the homework too. Now, there's some guidelines for integrals, right? And this one in particular is talking about when you have a sine function times a cosine function. Now, the main thing to note is if the power of the sine is an odd integer, all right, then you're essentially, and what's happening here is that they actually factor out a sine, all right? So again, if your power of the sine function is odd, then you're going to factor out a sine. And similarly, if the power of the cosine is an odd integer, then you're going to factor out a cosine, all right? So basically, I call this the odd man out rule, and I'll show you what that means. And then finally, if they happen to be even, right? If both the sine and the cosine have an even power, then you're going to use half angle identities, okay? Which are actually, they show you those right there. So let's go ahead and go to the first problem, right? So even though on this one we don't have a sine and cosine in this one, on this one we can actually use one of the double angle identities. Okay, so let me turn my notes to that so I don't mess this up. So essentially, all right, this identity says that sine squared, you can actually see it up here. That's what I'm going to write. Is equal to 1/2. I'm going to write this in black. I apologize. One half the integral on sine square of x is going to be replaced with 1 minus cosine of 2x. All right, if you wanted to, you can probably split this up into two different integrals where you have a 1/2 the integral of 1 dx minus 1/2 cosine of 2x dx. All right, and some of you eventually are going to get pretty good at this, and you're not going to have to do substitution for something as simple as this. But for now, all right, this side right here is just going to be, the left side is just going to be 1/2 x. That's not that big of a deal. But for the right side, what we're going to do, well, actually, I'm probably not going to write that first, is we're going to do substitution. We're going to call u is equal to 2x, and du is equal to 2 dx. Now, because I don't have a 2 in this integral in particular, then I'm going to divide both sides by 2. So dx is going to be replaced with 1/2 du. Okay, so this is going to be 1/2 times 1/2. That 1/2 that I just wrote came from the substitution part of cosine of u du. Now, the antiderivative of cosine is sine, okay? So this would be negative 1/4 sine of u plus c, all right? And then I'm just going to replace that u with a 2x. So essentially, the whole answer now will be 1/2 x minus 1/4 sine of 2x plus c. All right, so that's it for that. All right, so let's go on number 2. This is one of the more typical ones. So anytime I see a sine and a cosine function, and one of those powers is an odd power, in this case is sine, then I will do the following. All right. I will basically break this apart into sine of x to the power of 4 times the sine of x, which I'll write like this here in a second. So I'm going to leave that cosine alone. That's not going to change. And again, sine of x times the sine times sine to the 4th power of x is equal to sine to the 5th power of x, right? So that's how I got that. So again, those two are the combination of, sine of x to the 5th power is the combination of those two things that I just underlined. Okay, so now what I'm going to do now is I will use the Pythagorean identity to replace this right here. All right, so let's remember. Now I understand if you have to look up the the double angle identities, but you should at the very least write the Pythagorean identities up here and come up with them, right? So sine square of x is equal to 1 minus cosine square of x. All right, so this right here, I'm going to replace this sine with 1 minus cosine square x, all of that to the 2nd power, because remember, this right here that I'm underlining right there, that's sine square. And if I have sine square raised to the 2nd power, that's sine to the 4th power. Okay, so now the cosine square of x, I'm going to leave that alone. Sine of x, I'm going to leave that alone. And then now what I'm going to do is I'm going to use U-substitution. All right, so if I say that u is cosine, again, this are basically the steps they tell you at the beginning. I just think it's kind of confusing to look at them at first. So if I use U-substitution, the derivative of cosine is negative sine of x dx. All right, so I'm going to use U-substitution now, where 1 is going to stay the same, 1 minus u squared. This is going to be u squared, and sine of x dx, well, if I put a negative over here and I make that positive, I guess I can put the negative all the way out here. This is going to be, well, that's just going to be du. Okay? And before I integrate anything, I'm going to go ahead and expand this and distribute and whatnot. So this is going to give me a 1 minus a 2u squared plus u to the 4th. All right, so again, I'm just foiling at that point. All of that times u squared du. I can go ahead and distribute this. So I have u squared minus 2u to the 4th plus u to the 6th du. And I guess I wrote parentheses, but I don't really have to, I suppose. All right, so now I'm going to go ahead and integrate. Just add 1 to the power, divide by the same, right? So this is going to be 1/3 u cubed minus 2/5 u to the 5th plus 1/7 u to the 7th plus c. And then I'm just going to distribute that negative right there. And I'm going to write it in order. I want to write this negative 1/7. Instead of u to the 7th, I'm going to go ahead and substitute that cosine back. This is cosine to the 7th power plus 2/5 cosine to the 5th power minus 1/3 cosine to the 3rd power of x plus c. Now, I know what you're thinking. That negative, shouldn't that make that a negative c? Sure. But whether it's a negative or a positive, it's still a constant. So please don't get caught up in that. All right, so let's go to example 3. So even though in example 3, we don't have a cosine and a sine, this is a little bit different than this one, where if I have an odd function, I probably, or at least I'm going to try it, I'm going to break this down where I have one of the cosines like this. One of the cosines to the second power. Basically, I'm going to factor out one of the cosines out, okay? And then see what happens. Sometimes it may work, sometimes it may not. All right. Now, what we're going to do is we're going to use the Pythagorean identities again to replace cosine with 1 minus sine squared times the cosine of dx. And then now I will use U-Substitution at this point, where I'm going to call U to be sine of x. And some of you might be thinking, well, how do you know whether you should pick sine or cosine? Well, I can tell you that I picked the wrong one, and I couldn't do it. It was undoable. All right, so there's your answer for that, if you want to know. The derivative of sine is cosine of x dx. All right, so now I'm going to use substitution now. So I have 1 minus u squared. Cosine is just going to be, cosine of x dx is just du. Oh, that's great. So it's a pretty short one then. Okay, so after that, I'm just going to go ahead and take the antiderivative. So we have u minus u to the third over 3 plus c. And I'm going to go ahead and substitute that sine function back. All right, so there's that. Let's go to example 4. Again, use the rule of the odd man out. All right, so we're gonna grab that cosine and we're gonna break that apart into cosine square of x times cosine of x. And I'm gonna put the cosine of x over here. You don't have to do it like that, but that's what I'm doing. All right, and then we'll do from there, just like looks like we did the same thing in the last example at least, is we're gonna grab that cosine squared and use a trig identity. And then I'm going to use U-Substitution, where I'm going to call U is equal to sine of x, and du is going to be equal to cosine of x dx. And I'm going to use substitution from here. So we have 1 minus u squared times u to the fourth, and cosine of x dx is just du. Okay. I'm going to cut and distribute that u to the fourth. So I have u to the fourth minus u to the sixth du, and I'm going to go ahead and integrate now. So as you can see, this one's not too bad at all. I'm going to go ahead and distribute this. Excuse me, I'm going to go ahead and substitute back is what I meant to say. So we have 1/5 u was sine. So sine to the power of 5 of x minus 1 over 7 sine of to the power of 7x plus c. All right, so that's the answer for that. So as you can see, the one that you can really trust in all the time is just think of what I said. That's honestly the best way that I can remember the odd man out rule. If you have a sine and a cosine, always break up apart the one that's an odd between the cosine and the sine. Break it up. All right, so now we're going to talk about the guidelines for integrals involving only products of tangent and secant. This is I would say it's a pretty small subset, but nonetheless, if you have some of these, you can do them like what they're telling you. So the main thing to note on this, okay, is if the power of the tangent is an odd integer, all right, then you can try to factor out a secant and a tangent out of it, and which doesn't happen in these 3 examples. Don't know why. So love to show an example, but I don't have one. And on B, if the power of the secant is an even integer, then you're going to have to factor out a secant out of it. Okay, so again, kind of complicated it sounds like, so let's just do some examples, right? On example 5, we're almost kind of treating example 5. It's almost like the cosine and the sine, okay? If that's an odd number, if the tangent has an odd number, break it up. Excuse me, let me switch to black. I'm going to break this up into tangent square of x times the tangent of x dx. All right, so kind of starts off similar. And I'm going to use the Pythagorean trig identities, to figure out the rest, right? Here's one. I'm going to write it so you're not wondering where I'm getting this from. And again, I got these by what I've told you before, where I just have cosine squared plus sine squared equals 1. And I just divide one of them by cosine squared and get the answer for that. And I just do the same thing with the sine squared. And again, if you don't know what I'm talking about, you can just ask me when you see me. Right? But essentially what I'm trying to tell you is I actually don't memorize this. I can come up with them on my own, which is not hard. You can do it too. All right, so tangent square of x is going to be secant square of x minus 1. And well, the tangent of x dx is going to stay the same. Okay, so what we're going to do now, let's see. We want to distribute first. So we're going to distribute that tangent. So I have the integral of secant square x tangent x minus tangent x dx. Okay, so let's see what I want to do here. Okay, so at this point, notice that this right here, well, let me see. Am I gonna split it up? Just want to confuse you. Yeah, I'm gonna split it up. All right, so I'm gonna do an extra step here. Secant square of x tangent x dx minus the integral of tangent of x dx. You really don't want to split it if you don't have to split it, but my point is that this right here is at the beginning of the notes where I said you should probably remember these, or the notes that you should probably remember some of these integrals. The integral of tangent of x is the natural log of the absolute value of the secant function. So I'll put it on there for sure. As far as this stuff on the left, I'm going to say the u is the tangent. So again, you really got to know your derivatives and antiderivatives of trig function for you to be able to effectively do this. The derivative of tangent x is secant square x dx. All right, so I'm going to do substitution for this part. So this is going to be secant square x dx is actually going to be du, so there's that. The tangent of x is just u. And this part right here is just, I'm just going to keep it as the integral of tangent of x dx. All right, so the integral of u du is going to be u squared over 2. And I'm going to go ahead and just plug that tangent back into this equation. So I'm going to go ahead and substitute back. All right. And again, this part right here that I'm about to write came from the beginning of your notes. So I'm not really sure, if I'm being really honest, where they got this. I can probably research that for you later, or you can do your own research, but I guess you might as well try to memorize it or have your notes out when you do this. All right, so that's the answer for that. All right, so let's go over example 6. All right, and this is a little bit weird because both of these are even functions. Okay, so again, both of these are even functions. So on this one, I actually tried it both ways, and I could only do it one way. So again, if the power of the secant is even, well, I guess we're going to go with that. Okay, and then just see what happens. So if the power of the secant is an even integer, then we're going to try to split up that secant. Okay, so we're going to try to split up that secant. So here's how we do it. And notice that when they split it up right here, they actually split it up into secant square and secant square. So that's my goal here, okay? So it's going to be tangent of tangent of x to the 6th power. And this right here, I'm going to break this up into secant square x times secant square x dx. All right, now I'm going to go ahead and integrate, I'm going to go ahead and substitute some stuff out. So the tangent of x to the 6th power, and I will substitute this, or the middle one, it really doesn't matter which one you do, but only do one, with a Pythagorean trig identity. So this is going to be this. Okay, so again, I substitute this for this. And then now I will distribute tangent to the power of 6x secant square x. I will distribute that to both the tangent square x and the 1. So this is going to be tangent to the power of 8x secant square x. And then I'm going to distribute. So again, just to make sure we're on the same page here, I'm distributing that to this and to that. Okay. All right. So plus tangent to the power of 6x secant square x. Okay. So I'm just rewriting that part. Okay. So after we do all of that, then we're going to use substitution. And we're going to say that u is equal to the tangent. And the reason I want to do that, to no one's surprise, hopefully, or maybe you'll be surprised, I don't know, is because the derivative of tangent is secant square x dx, right? Which happens to be in both of those. Oops, excuse me. So now I will I will substitute this. So I have u to the 8th and secant square, and I forgot to put it. No, I didn't. U to the 8th. Let me see. Okay. I don't want you to be confused, but this is going to be u to the 8th, and this is going to be u to the 6th, and the secant squares that I could have factored out if I wanted to. All of that becomes, all those secant square dx, all those become secant square x dx. All right, so again, I could have split that up if I wanted to and put a dx here and then write another integral there, and that would have been the same thing, right? So I don't want you to be confused about what I'm doing. Okay, so that's the integral right there. I'm going to go ahead and integrate. Which is equal to 1 over 9. U was tangent, so this is tangent to the power of 9x plus 1 over 7. What is this? Tangent to the power of 7 x dx. Oh, what am I doing? X dx. I mean plus c. I let my mind wander. Whoop, I can't even write that c that close to it apparently. Okay. So there's the answer for that. Okay. Now let's go ahead and move on to example number 7. Now on this one, let's see if there's any idea here. The power of the tangent is so there's really no guidelines on this, and you'll see why. I actually try to do it the way that they did it. So this one doesn't actually fit any of that criteria that I have above on the page. The power of the tangent is not. I don't even have a tangent function here, so it doesn't even apply. And the power of the secant happens to be odd and not even. All right, so that doesn't really apply to this. It starts off the same though. Let me see here. So I'm going to start off the same way by splitting this up into secant square of x, secant of x dx. And let's see, what am I going to do after that? All right, so now I will probably, hang on. I should have looked at this. I did look at it and I can't even figure out what I did. Okay. Looks like they skipped a step in the notes. Okay, no. Okay, I didn't skip anything. All right, so what happens here, right, is that after that, I try to substitute like I've been doing secant square x with a trig identity. However, by the time I got to the end, I realized that I ended up, by the time I simplified everything, I ended up with exactly the same integral and I didn't solve anything. Right, so at that point, I had to think of some other stuff to do. And at this point, all we have right now, really, besides this, and since this is not a fraction or a rational, and then I had to think of integration by parts. All right, now, how do I know when I use integration by parts? Well, first think U-Substitution, because that might be easier. Right now, the derivative of secant is secant tangent, so that doesn't help me on this one. And then after that, you should think, okay, maybe it's integration by parts. Now, how do I know that this could be integration by parts? Well, first, can you set one of these to be u? All right, so you want one of them that's easy to take the derivative, and the other one needs to be easy to take the antiderivative. All right, so if I make u, like I said, be secant x, then the derivative of u would be secant tangent. Now, I know you don't see this on here, and that's fine. All right, and then now I'm going to pick v to be secant squared. Excuse me, I'm going to pick dv to be secant squared x. Why? Because I know that the antiderivative of secant square x, and this is a simple one, would be tangent of x. All right, so this is sort of a reminder of how to do an integration by parts. So that's how you can basically figure out, okay, this will work. Okay, so now, according to the formula, all right, just to remind you, it's gonna be u times v. So I'm gonna join those two together. So I have secant x tangent x minus the integral of those two right there. So I have secant square x tangent square x, right? Because tangent x times secant tangent is secant tangent squared. Okay. And then at that point, what I had to do from there is that I had to, again, I don't know the antiderivative of secant tangent, but now what I do know is that the secant tangent falls into this right here, where the secant has, well, wait a minute. Actually, it doesn't fit into either one of them. Secant power is a secant positive, and excuse me, I said an even integer. No. Tangent is odd. Okay, so no. Okay, so that doesn't fit, but here's what I figured out. If I distribute, if I substitute this tangent square of x into secant squared of x minus 1 dx, if I do that, okay, and I go ahead and distribute this, again, I'm just forced to write this over and over. So this would be the integral of secant cubed of x, and this minus will make this dx. I'm going to go ahead and split that up. Plus the secant. So again, that negative right there, that negative is going to make that a positive. So check it out. Remember that all of this was equal to the integral of secant cubed of x dx. All right, so what I'm going to do here is I'm going to add this term to this side, which is going to leave me with 2 secant cubed of x dx is equal to secant x tangent x plus the integral of secant x. And the integral of secant x is actually yet another of the integrals that I told you that you should memorize, or at the very least keep handy in front of you. So the integral of this guy right here is at the beginning of the notes. Okay, so that's what's kind of helps. So that's what I mean about keeping your notes at. I think that would really help you. All right, so notice that all I have to do now is just divide both sides by 2. All right, so the answer to this would be secant x tangent x plus the integral of this is actually the natural log of the absolute value of secant x plus tangent x plus c. Plus tangent x, absolute value, close that, plus c. All of that over 2. I guess technically, and I'm just afraid you might see it like that. They might write it where this only goes that far because, again, a constant divided by 2 is still a constant. Okay. All right, so I know that was a lot. This is actually just half of the notes. So I'm going to take a pause here, but if you want to keep going, I'm gonna put a video right here. Just a second, all right? So I'm going to pause here and move on from there.